Okay, so we're continuing this last example with energy for as it relates to energy approaches as it relates to rigid bodies. So earlier we found that the potential energy for all these systems could be determined in terms of what we were given. So for example, we're given theta, we're given L, we're given the masses M and so on, MC here. Those are all known quantities. So when we express these, the potential energies in terms of these, we essentially have the potential energies. Right? So the potential energy, total potential energy will be given by the sum of the potential energies of the bars plus the torsional potential energy stored in the spring. Right? This is when the bar has moved through an angle theta, when bar AB has moved through an angle theta. Now, we also found the kinetic energies of the bars. There's some things in the kinetic energies we don't know, right? We used our energy principles we learned earlier. But I don't know what the omega for bar AB is. In fact, that's what I want to find as a function of theta. I don't know what the velocity of the centroid at the centroid of bar BC is. This is V sub G. I do not know what the angular velocity of bar BC is, omega BC, nor do I know VC, the velocity of the column, after I've moved on a certain distance theta. So how many unknowns we got there? We have 4 unknowns, VC, omega BC, VG, and omega. So really, to solve this problem, I'm going to need 4 equations. When I do the energy relationship here, okay, so we figured out what the energies are, and we can apply the principle of conservation of energy when the angle theta is 0. So the system is completely vertical. So you'll see that your kinetic energy term will be 0 because it hasn't started moving yet, no velocity. And your potential energy terms will be given by the potential energy of each of the bars as well as the potential energy of the weight. We're talking about the weight potential energy now, gravitational potential energy. Each of the bars here, the weight of each of the bars times the height that they are from some datum, plus potential energy of the color, which would be its weight multiplied by the height that the color is from that same datum. And remember, now the system is vertical because my theta is 0. On the right side here, I have the potential and kinetic energy after the system has traversed some angle theta. So we're going to have some potential energy terms still, and we found those out earlier, right here. Right? So those are here, and I have my spring potential energy as well, here. And what are these? These are the kinetic energies we found earlier as well. And the unique aspect to this problem compared to what we normally do is that now we have some rotational kinetic energy due to both bar BC and bar AB. Note that where are these moment of inertias? Right? For bar BC, or not where they are, but they are being taken, the moment of inertia, about what axis? For bar BC, it's rotating and translating. So this term here, the I, is the moment of inertia about an axis through its centroid. For bar AB, we said this earlier, that this is the moment of inertia about an axis. It's rotating only, so this I is the moment of inertia about the axis through the point of rotation, and it's a fixed point, rotating about a fixed point. So we can look these terms up, or we can use the parallaxis theorem and get the moment of inertia about point A, a line through A, for bar AB as such. Alright, so we have all these terms, but this is still just one equation, so we have 4 unknowns. Remember, we wanted omega in terms of theta, so we really want to solve for omega. So where am I going to get my other 3 equations from? Well, we can use the kinematic relationships because that relate the velocities of 2 points on a rigid body that we did a few weeks ago, because that's all we have here. Our unknowns are all velocities, right? Velocities and angular velocities. So let's go here. Let's look at this diagram for a second. I could figure out, I can use some information here to help me move through this problem. What am I given? I'm given that this is a color, so it slides up and down vertically on this bar. So I can use the fact that this velocity is vertical only as a constraint. I also now have a pin connection here to a fixed point, so the velocity here is 0. So I could get some other equations, right? If I use my typical kinematic relationship between that relates 2 points on a rigid body. So easily I can see that, well, the velocity at B is going to be given by omega cross r, where r is the position vector from A to B. From A to B. So I can see the omega. I'm assuming that it is counterclockwise, some omega in the k direction using the right hand rule. So I get my omega AB as omega. And by the way, the velocity at A must be 0, right? And also, my position vector from A to B will be given by this distance here plus that distance. Negative this distance in the I plus this distance here in the J. Well, I know that the length of my bar is L. So if this is theta here, then this angle here must be theta. So if I'm going from A to B, I would have a minus L sine theta in the I direction plus an L cosine theta in the J direction. That's what we have here. Minus L sine theta in the I, L cosine theta in the J. I do that cross product, I end up with this expression. Now I know that the velocity at B due to bar AB, bar AB's movement, will be the same velocity at B due to bar BC's movement, because BC and AB are pin connected at B, so it's the same velocity even though it's 2 different bars. So anyway, now I can relate the velocity at C to the velocity at B, which we just found, utilizing that constraint that we know it has to be in the J direction. So I'm going to have something like this. VCJ is equal to velocity at B plus omega cross R, but the omega now is omega 4 bar BC. And the RC relative B is going from B to C. So I'm going to go, that's theta here. Again, we can do our magic, come over here. Then this length here is theta, right? So the RC, the R going from B to C would be L sine theta in the I and L cosine theta in the J. And that's where you see these terms here. L sine theta in the I, L cosine theta in the J. So I do my cross products, and I know that for a vector equation, if it's correct, then the J component on the left must be the J component on the right, and the I components on the left must be the I components on the right. So if we equate those components, we end up with the following. We end up with omega BC being minus omega BC being minus 2L omega sine theta. Now, that means that I've found 2 more equations, really. I found out what BC is in terms of omega, and omega BC is in terms of omega, which is, omega here is the angular velocity of the bar AB, which is what we're trying to find. So I do need 1 more equation, because that gives me 3 equations total. So I can get that, what was my other unknown? It was VG, right? So I can apply my kinematic relationship 1 more time here, using VB, which is known, the velocity at point B, which we know, and then using my omega cross product again. So we substitute for VB, substitute for omega BC, which is minus omega, and substitute for the position vector from B to G, G relative to B. So if I go over here, this time I'm just going from here to G. So I go to the right. So now it would be L over 2 sine theta in the I direction and L over 2 cosine theta in the J direction. That's where we have this here. So okay, I've done all of that, and then I now have a vector expression for VG. But remember, in the equation VG, in the energy equation, VG is a scalar. Right? So I don't have to really worry about equating I's and J's here. I can just figure out what the scalar value for VG is here. Because it's a vector, the scalar value is the magnitude of the vector, which is the square root of the x component squared and y component squared, correct? So doing all of that, now I have VG. I have VG in terms of theta and omega. So I have four equations. So between these four equations and four unknowns, I can substitute for VG, substitute for omega BC, substitute for VC. Alright, this was VC here, VC in terms of omega, omega BC in terms of omega. Now I have VG's magnitude in terms of omega. Remember, the thetas are given and the L's and so on. Those are just known values, right? So we play around with the algebra and we can make omega the subject of the formula to get this quite complicated expression.